This job aid is designed to help you collect mineral soil samples for bulk density analysis. After viewing this video, you should be able to follow the National Cooperative Soil Survey methods to independently collect samples using clod, core, and compliant cavity methods, and to match appropriate sampling methods to use for different site and soil conditions. Before you get started in the field, take time to review the Bulk Density Methods section of the Soil Survey Field and Laboratory Methods Manual, Soil Survey Investigations Report Number 51, Version 2, issued in 2014. Be sure to note that each method may be best suited to certain applications. A summary of the method is provided, along with any interfering conditions and safety considerations. Also note the equipment list, detailed procedure, definition of equation variables, and how to report bulk density values. Soil bulk density is the ratio of mass of solids to the bulk volume and is used to convert data from a weight to a volume basis. The value is essential for many soil data calculations. Because of this, it is essential to collect a quality sample of the proper size prior to submitting it to your lab. It is also essential to label the sample completely with a proper sample number and layer depth. Some sampling methods also require recording the volume of each sample.
We're out here today to talk about how to sample clods for the clod bulk density method that's widely used in the National Cooperative Soil Survey program. Bulk density is a critical soil parameter that affects about 85% of the soil interpretations in a major way, and so the measurement of its properties, of its values, is quite important.
The clod method is the preferred bulk density method, and clods are also necessary to measure soil water content at specific tensions, which produce data for estimating plant available water. Clod samples are also necessary to measure COLE.
And the objective is to extract a chunk, roughly the size of a potato, from the soil and keep it intact, and safely preserve it and transport it to the laboratory for analysis. To retrieve that sample from the soil, you first of all have to pick a representative site. It is the preferred method to be used, and it is widely usable across many soils, many conditions, but there are some circumstances for which it just isn't appropriate. One is where you have a lot of stones or gravel fragments such that it's difficult to extract an intact clod of appropriate size. Another is where you have extensive roots, particularly large roots. In the process of cutting those roots, oftentimes that will cause the sample to disaggregate in your hands. If the soil conditions are very dry, you may not be able to get out intact chunks. As a massive clod, they may tend to crumble to inappropriate sizes for this method. And if you have particularly loose material like sand, where there just isn't any coherency of it, it may not be appropriate to use this method. And if the layers are too thin, if you have something that's on the order of much thinner than 10 centimeters, 6 centimeters, anything thinner than that, it's simply not possible to get a clod of an appropriate size. Again, you may have to resort to compliant cavity or one of the other methods for obtaining bulk density if you have special conditions which simply preclude extracting an intact clod of appropriate size. So what we've got here is a soil profile that we've excavated, and it's broad so that we can see how it's done. Oftentimes this is done in a soil pit, but the process is the same. The first objective is on site is to identify the major horizons of that profile. We have them marked out here by white pins. And the objective here is to identify those horizons and then extract bulk density clods from within each of those horizons. So we've carved out several vertical grooves from top to bottom in advance in order to facilitate extracting the clods, and we'll show you the process in a moment. But the main point is that these are horizon-centric sampling efforts. So what we're going to do in a moment is we're going to carve out these chunks that are based on horizons, and we're going to then shear off those larger blocks, and from those blocks break out intact clods of an appropriate size, which will then be processed for shipping and handling. So how we're going to do that is use some sort of a carving knife or shovel to extract these deep grooves on either side. It's rather like collecting a soil monolith. And that's been done in advance. We're going to then take these horizon boundary zones and then cut those out further. It's very important and helpful, saves you a lot of time and trouble in this process, to sample from the bottom up. And that has several practical advantages. One of them is that as you extract these chunks for bulk density clods, there's a lot of debris that will accumulate in the bottom of the hole. So if you start from the bottom up, you don't have to continually re-excavate that debris. Another thing is that gravity will help in shearing off these larger blocks from which you extract your clods. It also avoids any contamination of material raveling down from up above. If you're working from the bottom up, you minimize that problem of potential contamination. Our objective is, in the end, is to end up with 3 clods for repetition in their measurements of bulk density, and an additional 2 clods if you are going to, at the same time, do sampling for thin section or fabric analysis. That's not always done, but so you can have 3 as a minimum clods for bulk density plus a potential extra 2 clods for a total of 5 extracted from each layer. So we want to go about the process here in a moment. We're going to excavate these zones, and I also wanted to point out that if you have very thin layers, this method is not appropriate. You simply cannot get a large enough chunk for a bulk density clod. But if you can, if these layers are thick enough, we're going to excavate out each one of these and get 3 or possibly 5 clods from each layer. If you have a very thick horizon, such as this lowest one, it may be so thick that you want to split it in 2 and in effect take clods from the upper part and from the lower part. A good rule of thumb is if a layer is more than 50 centimeters thick, you subdivide it into 2 different layers and get clods from the subhorizons. For the 3 bulk density clods, the orientation of the clod in its natural setting after when we extract it is not important. But if you're going to sample 2 clods for natural fabric or for thin section analysis, in that instance, proper orientation does matter very much. So a clod has to be extracted from in situ and its orientation maintained, so we know which end is up. And typically a pin or a nail or some other marker is then inserted into the top of the clod so that an orientation is maintained, so that when thin sections are prepared, they know which orientation is up. In a situation like this, where you have a thin layer which is still viable for extracting clods, but is on the thin side, as you work up from the bottom, if you remove the supporting column underneath, this upper unit thin layer may well collapse on you, so it's customary to go ahead and extract that one first so that it isn't in danger of being lost. For very large chunks of soil like this, if it's going to be moved off site to be prepped, trimmed, and whatnot, it's convenient to mark the top with an X or some other symbol so that orientation can be maintained if subsequent samples are going to be taken for thin section. Now that we've extracted our clods from the soil pit or the soil face, we typically transport them nearby to a preparation area where they will be prepared and secured to stabilize them for shipment to the lab for subsequent analysis. The process is going to involve taking the individual clods and first trimming each one down to an appropriate final size for dipping and then shipping. We typically take them, sample them, and extract them and cut them to a little oversized that they can be trimmed down to a little bit at the final stage here. Several clods have already been trimmed down to size to remove excess knife marks or any kind of debris that might be adhered to the outside of the clod, so that we have as pristine and intact a primary clod as possible. Additional clods here have not yet been trimmed down to size. These clods have to fit inside the cells in these shipping boxes. So we typically just use a knife to trim it down to an appropriate size, roughly the size of a very large apple or a potato. When carving the clods down to minimum size, it's important to keep alert for any cracks or defects that would cause saran to penetrate into the interior of the clod, which we do not want to do. If that happens, the remnants of clod should be discarded and an alternate one should be prepared. In preparing the clods for shipment, we typically dip them in epoxy resin to stabilize them and to prevent them from falling apart or from drying out in transport. That's done by taking powdered saran and dissolving that in acetone, and then dipping the clods in that solution and allowing that to dry, and then bagging that dried clod, that dried saran coated clod, and putting it in a box of appropriate dimensions. The saran comes in two different concentrations. The 1 to 7 is the standard one used for most loamy soils and clay soils. If you're dealing with very porous soils, such as sandy soil, sandy loam, something like that, a thicker solution should be used, a 1 to 4 solution of the saran dissolved in acetone. The acetone is commercially available at any paint store. There's no particular concentration. It's a standard formulation, and it can be obtained widely. It is a very flammable product, so some safety concerns should be very carefully maintained. Number one, no smoking, no open flame, because that stuff will go boom. The saran is typically dissolved into or added to the acetone in which it is stirred. It's not dumped in all at once because it does take a certain amount of time for the saran to dissolve in the acetone. Probably 15 to 20 minutes, all said and done. Equipment supplied by the Kellogg Soil Survey Lab comes with a standard complement of powdered saran of the appropriate mixture, empty tins to which you can add locally obtained acetone to dissolve the saran in. We also supply hair nets to hold the clods together when they're laid out on a drying line, and a stirring bucket and a stir stick. The clod dipping process is fairly straightforward. A hairnet, conventional hairnet, which is supplied, is used to support a clod. They're gently placed in it and then spun so that the clod is thoroughly supported. We're using, in this instance, because these are loamy soils, we're using a 1 to 7 saran mixture. The clod is supported from underneath your hands by the hairnet and simply dipped one time in the saran process, just in and out. Excess saran is allowed to drain off, and when you figure it's stopped enough, the clod is then transferred to a drying clothesline where it can be allowed to dry in the wind. After a time out in the wind and the sun, these clods should be dry. A quick test to find out if they really are To verify if they are not, simply touch the bottom of the clod, and if you don't get any residue on your hands, then it's dry enough to be bagged and tagged. So we take the clods off in order and make absolutely sure that they go in the properly identified bag and sell in the shipping box. The bags should be numbered with a sequential number of the samples that have been collected along that trip. The previous sample was collected elsewhere, so this is sample number 2. Clod is simply gently placed inside the appropriate bag, snugged up and tied off with a twist tie, and put in the appropriate cell. It's critical to get the proper data and number identification on the box and on the clod bag so that they can be matched up back in the laboratory. If that's not done properly, you've just wasted your time and you will get no data. It begins with labeling the soil survey sample ID number on the exterior of the box. So in this case, this is the soil sample from 2014 for Nebraska, from the county, FIPS number, and the actual number of the sequential order of the pedons that have been sampled. The clods then are matched up and also labeled on the interior so that you know that this particular cell contains a clod from that horizon. Clods are snugged comfortably into each cell, and empty cells are usually packed with newspaper or something else to help support all the other clods in the box.
Alright, I'm going to explain some of the core and the clod samples that we get here in the lab and give you examples and show you examples that are not so good, that don't give us very good data, and also some samples of some good clods that we like to get here in the lab. Alright, here's an example of bulk density that comes in. We have 3 ways that we can do this. We have either the can method, the core method, or compliant cavity. These samples come in a sealed bag, and the information that we like to see on the front is the pedon number, the horizon designation, the horizon depths, the name of the site, and also the volume of the sample needs to be on the front of this bag. When you take the 3 separate cores from the layer, they need to be individually bagged. Some of the clod samples that we get in that do not give us good data. Here's an example of a clod that is crumbly, and as you can see, the saran here will get stuck in these little air spaces, air pockets inside this clod, and when we put it onto the table, the water isn't free to absorb up into the clod. And of course, these pieces we can't use anyways, and if we break these pieces apart, the clod wouldn't be big enough to use. Here's another example of a clod that we've gotten here in the lab, and you can see that there may be some tool marks in it, these flat surfaces in here, and that could lead to compaction for these clods and give us abnormal bulk density results. Also, this clod is too small, and it has these thin areas and these peaks that we don't like to see. Here's another clod that looks like an O horizon. As you can see, the sticks and twigs, there's a lot of air pockets in here that if we dip this in saran, it's already been dipped in saran, so these saran go right into these air pockets, and it's full of saran, and we don't get good bulk density with these. This would be more of a compliant cavity. Here's a couple clods that came in that are just definitely too small. There's nothing that I could do with this clod here. It wouldn't give me good results. Here's a clod that has come in that's a sandy texture, and the clod probably looked fine in the field, but when it was transported, it broke in the box, and then we kind of have it just spill out because the clod has broken that saran on the outside, and all the soil inside is disturbed, and we can't use this clod. Another thing with these clods is when they do come in, if they do make it through that transportation, then oftentimes we have problems with these fall apart when we do saran dips in the lab, and when we cut them on the saw to make that flat edge, they also come apart. The contents will fall out during that part, and then the clod is not usable. Here's another clod that has a gravelly texture. It looks like a nice clod from the outside, but I have cut it open here to show you what happens when these loose texture clods are dipped in saran. As you can see, the saran has penetrated almost this entire clod, leaving like a solid outer casing and a very small portion of loose material in the center. These types of clods give us a misrepresentation of the bulk density, and for this kind of clod, compliant cavity would be a more suitable way to sample. What we're looking for in our clods is a potato or a fist-sized clod. It doesn't have any loose or smaller clods on the outside. We're looking for a clod that has a more smooth, rounded exterior. If you have these peaks and edges, carefully carve any peaked edges away. Keep in mind the texture and soil that's being sampled, and then decide what sample method to use.
So one of the things that you can do before going into the field and performing the core method would be to measure the known volumes of your cylinders. For example, with a core, if you have the volumes already measured out, when you go into the field, you can go ahead and label your bags in your data sheet. This is pretty useful, especially when you're using different cores that have different volumes, as not to confuse the volume for data analysis. This particular method is a pretty simple method that you can do if you're unable to take a clod sample. Using the core are really good for soils that have high field capacity, low extensibility, subaqueous soils, as well as soils that are sandy. Some of the equipment or tools that we need to perform this particular method are a sharpshooter, a sharp knife, sealable plastic bags that are labeled and large enough to hold your sample. The core method is not suitable for soils that have rock fragments, coarse roots, or hard and or cemented soil layers. Due to soil variability, make sure to take a minimum of 3 cores per soil layer. Each core should be placed in its own bag, labeled with the site ID, the volume, as well as the depth. So in summary, one of the things that you'll do will be prepare a smooth, undisturbed surface, whether it's horizontally or vertical. A tool that we use in the field to sample for bulk density is using the known volume can, which you can request from the KSSL laboratory. We provide cans with known volumes labeled on them. These cans are very useful for soils where you can't get a clod and you have trouble probably getting also a core. This is done preferably in very loose soils. And similar to the core method, you press it into the face of the soil wall at the selected depth, either horizontally or vertically. You will use the palm of your hand and press in gently until the can is full. Once the can is entered into the soil, then similar to the core, you will dig the can out, smooth the surface, and place into a labeled, sealed bag.
This method is also adapted to measure satiated bulk density in subaqueous soil samples collected with vibrocores and opened by cutting. A plastic syringe with the end removed is used to collect a mini core. The plunger can be fixed at the 10 milliliter volume mark and the syringe gently pushed into the split vibrocore sample to collect a known volume of sample. The moist sample weight is recorded. The sample is then dried in an oven and weighed. The difference in weights, along with the known volume, gives the satiated bulk density.
So today we're going to demonstrate a bulk density method, and it's the compliant cavity method. And this method is good for if you got a thin layer that you want a bulk density of, where the soil is loose or it falls apart easily. Or maybe you can't get a clod out of it, or you can't get a core out of it. An advantage of this method is that you don't have to smooth the surface before you do the bulk density method. It'll handle irregularities in the surface. Okay, this method can also be used if you do have some rock fragments present. You don't want too many rock fragments, and usually you want them pretty small, gravel size. Because if the rock fragments get too big or you get too many, you won't be able to get enough soil to really get a good representative sample for a bulk density. The surface should be horizontal. You can use this in lower depths. You just got to dig down and smooth out a surface, and then you can do the compliant cavity method in different depths. The equipment that you need to do the compliant cavity, you're going to need a plastic ring, a foam ring, and you're going to have 3 threaded rods with wing nuts on them. That's to help holding the ring in place. And you're going to have a hook gauge, and that's going to be used to measure your datum, your reference point. And then you're going to have some plastic film, and you're going to have some water. And you're going to have 2 graduated cylinders, a 1,000 milliliter cylinder and a 500 milliliter cylinder. And to pound in the rods, you're going to have a mallet. And you may need a spoon to help dig out the soil, to excavate the soil. Once you've removed all the material off the surface, you're going to place the plastic foam on the soil. And then you're going to place the plastic ring over the foam. And you're going to take the 3 threaded rods, and you're going to pound them in and try to secure that ring in place. So you're going to use the wing nuts and screw them down, and so that the plastic ring is firm in place. You don't want it too far down, but just so it doesn't move. Now we're going to measure the head space of this cavity, and we're going to take a plastic film, put it in the cavity, and make sure it conforms to the surface, to the bottom, to the sides, and we don't want any tenting. So we want to make sure it conforms to the sides and to the bottom. Then we're going to use the hook gauge, and we're going to place it on the ring, and we're going to put it, so it's secured against these 3 plastic bars that are here. And you're going to have to remember exactly how you placed it, the direction of this hook gauge. Okay, now you're going to add some water to it. So you measure out some water. We're going to start with 500 milliliters, and we're going to put it inside the cavity. And we're going to fill it up till it's the top of the hook gauge. So this is where you want to make sure that that plastic conforms to the surface and to the sides of the cavity. And once you've got that water level right to that tip, then you measure the amount of water that's in your graduated cylinder. And you subtract that from the 500, and then you'll have the volume of the water of the headspace. And that's what you need to record on your data sheet and on the bag. Okay, so then we remove the hook gauge, we remove the plastic and the water. Now this is where we're going to excavate down and collect the sample. So you'll need a spoon and a plastic bag, a sealable plastic bag that you're going to put the soil in. So you're going to dig down, 2 to 3 inches and excavate out the soil, and you want to dig straight down on the sides so you get a good representative sample, of the soil. And you're going to be putting it, take the spoon and dig it out and put it in your plastic bag. Okay, one of the key points to remember is when you're taking your sample and digging down, you want to dig down to the depth that you want to measure bulk density. If it's 2 inches, 3 inches, you dig down to that level, whatever level it is that you want to take your bulk density. Then we're going to measure the cavity space again. So you're going to take your plastic, place it in the cavity. Make sure it conforms all the way to the sides, covers every square bit of cavity. Then you're going to take the hook gauge, place it exactly the way you had it before in the first time. The hook the same direction, put it on the ring, make sure it's secured exactly the way you had it before. Okay, then you're going to measure, you're going to need more water this time. So you may want to use the 1,000 milliliters, but I like to use the 500 mils. And if I have to, I'll fill it twice. So I'll take a 500 mils and I'll fill the cavity. Usually it'll take the whole 500. Then I'll fill up the graduated cylinder again with another 500. And so then you'll add more right to the tip of the hook gauge like you did before. And make sure there is no tinting, and the water, the plastic, everything conforms to the sides and the bottom. And if you overfill, you can use the syringe and take some in and out until the water's level is right at the tip of that hook gauge. And if you do take some out, remember to put it back in the graduated cylinder so that you can measure that. Okay, in summary, what you're doing for the compliant cavity is you're measuring the volume of the head space, of your cavity there. You're using water to do that. And then you dig down, take your sample, and you're going to measure the cavity again with water. And the difference between the initial volume and the final volume, that is your sample volume. And then you just remember to record on the bag and on your data sheets the initial and your final volume of water.
An experienced soil scientist can help you select the proper method and technique for collecting bulk density sampling. This job aid is designed to help you match the appropriate bulk density sampling method to various site and soil conditions. The clod bulk density method is the most widely applicable method and is the preferred method because clods have the advantage of being used to produce water retention data and to measure COLE. These items cannot be measured from samples collected by the known volume can or compliant cavity methods. As with any new skill, proficiency comes with practice. For more information and tips on sampling soils, please see our online NCSS training materials.